Hi everyone! For our project, we did an optimization problem on Black Friday shopping inspired by the holidays. My name is Liz.
I'm Matt.
And I'm Olivia.
And this is our project. We created a wish list of 10 items that are on sale for just one night. These items are found at many different stores and we may not have time to visit all of them. With a time constraint of 1 hour and 45 minutes, we prioritize the items on our wish list using a preference rating. The scale goes from 1 to 5, 1 being less desired and 5 being highly desired. We need to maximize the sum of the preference rating of the items we can buy given the time constraint. Here you can see our rating for each item on our wish list, as well as the index for each item used in our code. Our objective function maximizes the sum of preference ratings of the items we are able to purchase. Item sub k is a binary variable in which 1 indicates that the item was bought, and therefore the rating is added to z. When item sub k is value 0, we did not purchase the item and its preference rating was not added to the objective function.
As we mentioned earlier, we have a limited amount of time to shop, 1 hour and 45 minutes. This time is further constrained by the amount of time it takes to travel from one location to another, as well as the time it takes to wait in the checkout lines at each store to purchase the items. In addition, some items on our list are only available at one store, while other items are sold at numerous stores. Here's a map to help illustrate the problem. The time in minutes it takes to travel between locations is shown among the dotted lines, and the wait times for each store's checkout line is displayed in red on the store window. The items on the wish list that each store contains is listed under each store. As you can see, Target has the most items to offer of any other store. However, it also has the longest wait time. So our program may decide to travel to numerous stores with short wait times instead of going to just one place. Some stores are in complexes while others are in standalone locations, such as Apple. Our program states that it doesn't take any time to travel between stores that are within the same complex. We use 2 other variables in the formulation of this problem. Each store is represented as a binary variable, where 1 represents the store being visited and 0 represents the store not being visited. Each path between locations is also represented as a binary variable, where 1 represents a path from A to B being traveled and 0 represents a path not being traveled. If a store was visited, then the items at that store are purchased and accounted for in the objective function. Additionally, we incorporated a constraint in our code that checks that the summation of the commute times for each path plus the summation for time waiting in line spent at each store visited is less than or equal to the allotted time of 105 minutes.
So here we have the results of our optimization problem. As you can see, the optimal value here is 21, which means that we purchased items that sum to a total preference rating of 21. The next part of our output is the item vector. This vector is indexed according to the item numbers in our wish list, so it can be easily interpreted. Here we have purchased items 4, 5, 6, 8, 9, and 10. Similarly, we have a store vector that tells us which stores we visited. So these would be stores 1, 2, 4, 7, and 8. Finally, we have a path matrix, which I will explain in the next few slides. So now we will take you through our journey visually. We started our house, which is indicated in our output by a 1 in the first element of the store vector, as mentioned earlier. In the first row of our path matrix, we find a 1 in the 7th column, which draws a path from location 1 to location 7. So upon leaving our house, we travel the 12 minutes to store 7, where we buy item 5, dog food. We wait just 6 minutes at PetSmart to buy this, and we get a 2-point boost in our optimization function. We check this item off the wish list and move on. Next, we observe the 7th row of the path matrix, where we see a 1 in the 8th column. So we walk over to Bed Bath & Beyond, which is store 8, and purchase items 8 and 9. Now, inspecting row 8 of the path matrix, we find a 1 in the 2nd column. This means we travel to store 2, which is Apple. Here we purchase items 6 and 10 and continue on our way. We don't have too much time left to shop, so let's keep moving. Now we travel to Walmart to buy a nice Christmas tree for the holidays. This is indicated in our path matrix by a 1 in the 2nd row and 4th column, indicating that we traveled from store 2 to store 4. Once again, we check this item off our list and check the time. We're almost out of time, so we must head home. With just 17 minutes remaining, we make the 15-minute trip home from Walmart. This completes our path and is indicated once again by a 1 in the 4th row and 1st column of the path matrix. We weren't able to purchase all the items on our wish list, but we sure made the most of our trip.